All right, we're back to Streams, and we have a little problem to fix. And to test this a little more, and some more exercises with lazily evaluated streams that will test and enhance your skills. So let's get back. Cool, so we're back in the IDE, and we have a little problem with flat mapping on our lazily evaluated streams, which means that we've made a mistake when deciding whether an operator is actually lazily evaluated or not. And the problem seems to be with flat map. So let's take a look at what flat map does. And flat map does f head plus plus tail flat map f. Now, what does plus plus do? Well, plus plus says that it evaluates the another stream and then it constructs a new cons. So the problem here is that flat map is evaluated recursively too many times and it causes a Stack Overflow error. Now, the reason why it would cause a Stack Overflow error is because this expression over here must be eager evaluated, so not lazily evaluated. So it must be that our operator here does not preserve the lazy evaluation. So let's take a look at how the plus plus is evaluated. And if we take a look at the parameter here, of course it does not preserve lazy evaluation because the parameter is eagerly evaluated because it's not called by name. If it's not called by name, then the operator here will evaluate the parameter first before evaluating the entire expression. So before evaluating flat map, then this expression will evaluate tail flat map first before evaluating the giant flat map. But what does flat map do? It evaluates flat map. What does flat map do? It evaluates flat map. And so on and so forth on the stack until the slack blows in our face. So the plus plus operator here needs to be called by name so that we can delay the evaluation of tail flat map until it's needed. So with this knowledge in mind, let's right click and run this again. And the compiler complains, oh, because we just modified the plus plus operator in the non-empty stream, but we need to modify the method signature in the trait and in the empty stream implementation as well. So in the abstract class, I need to modify the plus plus operator to take a by name my stream, and in the empty stream as well. All right, so if I right click and run this again, then I should not be getting any problems again. So as you see, we have the proper flat map implemented because now plus plus maintains lazy evaluation. Cool, so let's get back to our tests. And let's try the filter functional as well. So if I print line start from 0 filter, and let's just filter out, just filter in only the elements that are less than 10, and then I try to take, let's say all the 10 elements, and then I say to list. All right. And I print this out to the console. I should be seeing all the elements from 0 to 9. And the take 10 here is optional because the stream here is finite now. So I've turned an infinite stream to a finite stream by filtering it to a simple condition. So I should be seeing, the filter now throws a Stack Overflow in our face. So let's figure this out. So what happened? Stack Overflow error on filter. Now, to be honest, by looking at the filter implementation here, because all these expressions here are lazily evaluated, if I think a little bit further, this is actually my mistake because this is an infinite stream, and filtering an infinite stream with a function does not guarantee that the stream is finite. I have no way of knowing beforehand whether this expression is a finite stream. So the computer actually tries going through all the possible naturals and trying to see if they're less than 10. So the filter has good reason for blowing up in our face. It's not because of our program design, but it's because of the way that we wrote our test. All right. So the take 10 is actually legit here. Now, be very careful if you try to take more elements from this filter, like say try to take 11, this will still crash in your face, because after taking the first 10 elements, the computer will try to find out the next element out of the stream of naturals, which is less than 10. Obviously, it's not going to find it, but that doesn't stop it from trying. So this will still blow up in your face. But if you do want to test the edge case that you want to take more elements that you have available in the stream, then you can simply say take 10 and then try taking 20. And this will work because take 10 is a finite stream, and taking 20 out of a stream with just 10 elements will just return you those 10 elements. So if I right click and run this, I should be seeing, of course, the list 0 to 9. Cool. So given all of these tests, we can conclude that our streams run well. We've tested basically all the functions that we wrote. All right. Now, given the streams that we implemented, I want you to do 2 more exercises on streams. This time, the exercises are going to apply on already implemented streams, so I'm not going to ask you to enhance the streams further, but just use them. All right. So first exercise is going to be the stream of Fibonacci numbers. This is quite a tricky exercise. The implementation is straightforward, but thinking about it is not. All right, so how would you implement the infinite stream of Fibonacci numbers? Think about it. The second exercise is also even harder to think, although the implementation is, again, just 2 or 3 lines of code. Try to implement the stream of prime numbers with an ancient method called Eratosthenes sieve. So how does this work? Eratosthenes sieve starts with the natural numbers from 1, 2, 3, and so on. Actually, in practice, just start from 2 because 1 is not considered to be a prime number. So 2, 3, 4, and so on. And the technique goes like this. The first step is filter out all numbers divisible by 2, which leaves out 3, 5, 7, 9, 11, and so on. Then the next step is actually keep the 2 because 2 is also a prime. All right. Then filter out all numbers divisible by 3. So from this part on, just filter out all the numbers divisible by 3. So you're ending up with 2, 3, 5, 7, and you leave 9 out, and then you have 11 and 13, and then 17 because 15 is divisible by 3, and so on and so forth. Then filter out all numbers divisible by the next number left in the Eratosthenes sieve, which is 5, and so on and so forth. So you get the stream of all the prime numbers in this fashion. So I want you to implement the stream of prime numbers by applying this technique. So I want to warn you that these 2 exercises, the Fibonacci and especially the Eratosthenes sieve, are hard exercises. So if you don't find a solution, don't worry about it. Even though the implementations are quite straightforward in the sense that they're concise, they're not easy to think about. But if you have the time to take on a challenge, please take whatever time you need to think at this exercise, because if you get this on your own, you will never forget how to work with streams, I promise you. All right, so pause the video and I'll come with solutions in a few moments. Cool, let's start with the Fibonacci. We're going to define a method called Fibonacci, and this will receive 2 parameters. The first number, which is an int, and the second number, which is an int. And this will return a my stream of int. All right, so the attempt here is to call Fibonacci with 1 and 1. And then if we want to take 100 numbers of Fibonacci, that's fine. And toList. So this is the final call that we are going to use when printing the Fibonacci numbers. So how does Fibonacci actually work? Let's break this down. In general, the Fibonacci function here is going to return the stream of the Fibonacci numbers starting with these two numbers. But how does this work? Remember, we are returning a lazily evaluated stream. So the Fibonacci of first and second will obviously be a stream starting with first and something. So remember, this expression is lazily evaluated. Now the question is, what value does this expression have? Well, of course, this will be another stream, all right? And this other stream will be a recursive call of Fibonacci. So we should return a cons of first and the recursive call of Fibonacci with the next first two elements. What are the next first two elements? Well, are going to be Fibonacci with second as the first element of the tail, and the second is going to be first plus second. All right. So this is going to be our implementation. So we're going to return new cons with first, and as the lazily evaluated tail, Fibonacci with second and first plus second. And that, my folks, is it. This is Fibonacci. And if we right-click and run this, if we take the first 100 elements, we're going to see a lot of Fibonacci numbers. So 1, 1, 2, 3, 5, 8, 13, 21. So this is the Fibonacci progression, and this goes all the way to the end. And we're seeing some negative numbers here because Fibonacci is an exponential series. So it will quickly run out of the integer representation. If we run with big int instead, then we should see like proper numbers. All right, so now we have these gigantic numbers with Fibonacci. We can take as many numbers as we want. All right, so this is the Fibonacci representation. Again, very simple or very concise implementation, but very hard to think about. All right, so that was the first. The second is even more complicated. So Eratosthenes, sieve. Now, Eratosthenes is going to be as well a method. Let's put in a proper spacing here. So Eratosthenes, and it will receive a stream of numbers as a parameter. So myStream int, and it will return a myStream int. So the job of this Eratosthenes method is to sieve the numbers passed in here as a parameter. And the implementation is going to be as follows. If numbers is empty, then just numbers. If this is a finite stream, or if I'm at the end of a stream, then I'm just going to return that. This is very simple. Otherwise, and here's the crux of the implementation, I'm going to return a new cons with numbers head and something. Now, what this something is going to be, let me break this down. If I have the numbers, the natural number stream as 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say 11 and 12, and so on and so forth, right? And I want to apply Eratosthenes on this stream. Now, what do I get? Now, the critical idea of the technique is that at every iteration of the Eratosthenes sieve is that at every iteration, the head of the stream of numbers being processed must be a prime. So what I end up with is the stream starting with 2 and Eratosthenes applied to the rest of the stream, filtered by those that are not divisible by 2. So I end up with 3, 5, 7, 9, 11, 13, and so on and so forth, which in fact is 2. And the rest of the stream is Eratosthenes applied to numbers filtered by n mod 2 not equal 0. Alright, so I filter those out, and then I apply Eratosthenes again on the stream starting with 3. And at the end of that iteration, I'm going to end up with 2, and then this guy will be 3. Alright, so I'm just going to write this like that. So I'm 2, 3, and then Eratosthenes applied it to the rest of the stream. So Eratosthenes applied to 5, 7, 9, sorry about that, 5, 7, 9, 11, and whatever was left here, filtered by n mod 3 not equal 0. And so on and so forth. So I get 2, 3, 5, and then Eratosthenes applied to the rest of the stream, filtered by n mod 5 not equal to 0, and so on and so on. All right, so the tail here is going to be Eratosthenes applied to numbers tail, so this guy, filter, and for every n, we say n mod numbers head not equal to 0. And this is the implementation. And just for our shorthand, we can simply write underscore mod numbers head not equal to 0. This is very hard to think about. If we then say print line Eratosthenes applied to my stream from 2, and then the underscore plus 1, so all the numbers, all the natural numbers starting from 2, and then if I take the first 100 primes, then if I print that to list, then I should see the first 100 primes printed to the console. So as you see here, we have 2, 3, 5, 7, 11, 13, 17, 19, 23, and all of these seem legit. So 127, 109, all of these are primes. Okay, so this is the stream of primes by applying an ancient technique on infinite lazily evaluated streams. Like I said, these two exercises are very hard to think about, even though their implementations are basically one-liners. If you manage to write these implementations or similar implementations by yourself, I am stoked. You rock. I promise you, you will never forget how to work with lazily evaluated streams. Alright, so this is the end of another important topic in advanced functional programming. I hope you had fun and found this couple of videos useful. I am Daniel, and I can't wait to see you in the next video.